Hello! Hey, year 10s, good to see you. Right, bonding lesson 12, only 1.5 more lessons to go. Ian is the first one in. He is the first one in the house. Let's go to share screen. That one. Right. We've got, you got an advantage. Right. Title is Graphite. Oh no, it's lesson 11. Oh no! It's not lesson 12, it's lesson 11. GCSE bonding. Whoops. No, bonding. Lesson 11. Graphite. I'll have to change it on my channel. Graphite. Not doing very well on my typing today. Oh, there we go. Learning objectives. I'm going to take them directly off my YouTube channel because it makes more sense for me to do that because then there'll be similarities. It's nice to have continuity. There we go. We're up. We're up and running. Graphite. Boom. So, number one, no graphite properties. I'm going to disconnect my other screen. Oh, I can actually have my YouTube channel up on the other screen. Check that. I can see the chat then. Ooh, ooh, ooh. I'm gonna go grab you.
I can actually have my YouTube
channel
on the other screen.
I'm sorry.
I can see the chat.
Oh no.
Ooh, ooh, ooh. I'm gonna go grab.
Okay, let's get rid of that. Sorry about that, guys. Making all kinds of horrible noises. The sound laggy. It sounded laggy to me. Sounded laggy. Laggy. No. Okay. I'm trying to connect my mouse. Mouse isn't working. Actually, it was. Right, I've got my mouse up and running. Swing that over to there. Pop out the chat. Pop out the chat. There we go. Then get rid of that window. Yay. Okay. We're in. Right, graphite. Okay, number one, know the properties. Number two, understand graphite structure. Number three, be able to explain properties of graphite from its structure. And number four, know its derivatives. Hi, Nita. How did your exam go? Let me know. Right. Now, can you sew? Can I sew? Can I sew? What are you saying, Nita? Can you sew? Great. Oh, I'm so glad, Nita, it went well. So glad. Right. Guys, graphite. Okay, so the exam went great. I'm so glad. So guys, today's lesson for graphite. It's funny because I've got my tablet set on pencil. It even looks like graphite. It's funny. So graphite is one of our giants. So number one, we have to know that it is a giant. It's one of our giant covalents. Giant covalents. But it's very special. Graphite has its very own set of stories. And because graphite is so special, I need to do it as this independent lesson. Can you solve the Edexcel paper IC Jan 2020? Mita, there was a reason why I didn't do that one because I thought some schools might be using it for their mocks, which I'm assuming yours did, so I'm glad I didn't. And I'm very wary of doing it, Mita, very wary. I'll get lots of shouty teachers at me, so maybe not quite yet. Okay, so number one is we know, so facts about graphite that we already know, facts. Number one is it is carbon solid. It's nice to see our state symbols appearing there. So we've got carbon solid. It is similar, of course. It's now diamond is also made of pure carbon. They are made of exactly the same material, and they are said to be allotropes. So diamond looks like diamond. Diamond and graphite. I don't know if that's the right way round on that particular thing. Diamond and graphite are called allotropes, which is quite a nice name. I mentioned this last time. Yeah. They have the same formula, but different structure. Yeah. Same molecular formula. By the way, it's actually an elemental thing, this. So same, I'll put same formulae. You shouldn't really do that. It's same element, different structure. That's better. That's a better one for allotropes. Different structure. There are other elements, by the way, that actually fit into that can have allotropes. Phosphorus is one of them. Phosphorus can do all kinds of funky stuff. And there's 4 different versions of it, which is kind of funky. Sulfur can do it too. Sulfur can do cool things. I actually do a demo of sulfur if you guys are here. But we know that number 1 is that graphite is made of carbon. Number two, graphite. Graphite is gray-black. So it's nice to pick up its colors. Gray-black solid. I'm actually just going to put state symbol. Gray-black solid. There we go. It's nice then to realize that diamonds, of course, are completely see-through. It's quite nice to always talk about that as well. The next thing is we've met graphite before, used in pencils. Used in pencils, and the electrodes for the electrolysis of aluminium. I'm just going to put a formula of aluminium oxide. There we go. Okay, so I think what we can now do is we can now pick up the dog water. Peck's drawers, I'm about to remove you. It just seems a really stupid thing to write. I'm assuming you're 6 years old. Excellent. So what we can pick up now, I'm actually going to remove him straight away. He's going to post something horrible. Remove, hide, remove. There we go. Done. So properties. So graphite is special properties. So we've got number 1, it has a melting point of 4,000 degrees Celsius. Like, that'd be crazy. Yeah, it's an incredibly high melting point. It's only a few degrees lower than diamonds. It's incredibly high. And we'll need to run Susan Boyle on that because it's very special. All of graphite has an entirely separate set of stories. Number 2 is it's soft. Now, isn't that weird? It's soft. Yeah, now that's strange because if you've got a melting point of 4,000 degrees Celsius, you would expect to be incredibly hard, but graphite has a very odd property of being soft, hence why we use it in pencils, which is kind of nice. Number 3, it conducts electricity. It conducts electricity. No other giant that does that. Silicon does a little bit, but silicon is a semiconductor. It's a bit of an odd one, silicon. There's no other standard giant covalent that conducts electricity. It's very strange. Conducts electricity as a solid. Really weird. And those are the only properties. Oh, it's also brittle, by the way. But brittle, I've never actually, just to flag that one, I've never seen them ask a question on brittality. So you can kind of ignore brittle, even though it's nice to talk about. That's why your pencil, when you drop it, you shatter the lead. Yeah, it's a very brittle substance. And it's funny that it can be brittle but soft at the same time. Very interesting. Remember that brittle is the opposite of malleable. Yeah, malleable means that you can bend and shape something as a solid. In graphite, you definitely can't do that. So what we now need to do is, now that we've got the properties, we now need to investigate its structure. So we can put a new subheading of structure. So number 1, it is made of pure carbon. So all the atoms here are carbon. But graphite is kind of special because in graphite, you've got 2 images. Number 1, you've got, I'm going to put diagram number 1. Diagram 1 for graphite. And it is this. So the first one is that graphite forms in layers. Forms in layers. This is why it's soft. This diagram here explains why it's soft. Yeah, so this one here we can add an explanation to. So the question is, explain why graphite is soft. Explain graphite soft. I'm just keeping it simple for your notes. Yeah, answer, forms in layers, and those layers can slide, just like metals can. Next, so that's diagram number 1. Diagram number 2. So if we were looking like, this is where it'd be really useful if I had my camera. We were looking before with this picture here. If I drew a pencil, yeah. We were looking at the lead here. Sorry, the graphite. What we'd realize is that we're looking at it like that. Yeah. So we're taking like a vertical cross section through it. Yeah. In diagram number 2, we're going to change our position. What we're going to do is we're going to look at the graphite now from above. So instead of looking at it from a sideways view and seeing the layers in graphite, what we're going to do now is look from above, and we're going to be looking directly down on top of one of those layers. And this is where we're about to see the carbon atoms. So here's what it looks like. There's a carbon, there's a carbon, there's a carbon, there's a carbon. So each of the spheres is a carbon atom. And what we notice is that graphite forms in a very distinct shape. It forms in these hexagonal, I haven't done that very well to be fair, forming these hexagon style layers. I'm trying my best to draw a decent picture of this. Really, I'm trying hard. Oh, a bit too, I'm gonna zoom in. So graphite has this really lovely honeycomb-like structure, and it goes on forever. These layers are giant, millions of carbon atoms, all linked together in one giant sheet of graphite. So we're now looking down on top of the layers. That's what we're doing. There we go. Draw another one up there. There we go. So these layers go on indefinitely. They just go on and on and on. I want to get rid of that guy up there. I don't like him. Oh, no, I'm going to change my mind. There you go. So these layers just continue on forever. Hence why it's giant. So we form, sir, can you solve the Excel January 2014 whenever you have the time? Feffy. Feffy Green. I'm happy to. I will do the Jan 14 paper for you this weekend. No problem. So we're looking at the sideways view with the layers, and then we're looking at the above view, for on top of the layers to see the structure. Now, what you realize is that this is very strange. Diagram number 3. Diagram 3. Now, what's strange is that each carbon atom is actually forming only 3 bonds, which is very strange. Each carbon atom is only making 3. And you can see this if I just pick out any particular one. If I pick out him, he's forming only 3 bonds. Now, this is very strange. Now, we can turn this picture into a dot and cross diagram. Rather than stick, we can do dot and cross. And here's the new diagram. This is actually diagram number 3. Now, this is really odd. The reason why this is strange is because what you realize, do you know what I'm actually going to do? We're going to, rather than do it in the trigonal planar picture, where rather than doing it like this, I'm just going to draw it like this for a minute, and you'll understand why in a second. I'm going to draw it like this. The reason being is you're going to notice something. So carbon has 4 electrons in its outer energy level. We know this because of my gorgeous, beautiful periodic table. Yeah, carbon is in group 4. So it has 4 electrons in its outer energy level. And what it does is it will link to 3 other carbons and form, very strangely, it will form 3 covalent bonds, which are incredibly strong. But then it stops. Now, the reason why it stops is because this 4th electron now hops off. So I'm just going to do this like that. There we go. The 4th electron hops off. So what is happening here is, let's put this into bullet points, and you're going to need these. Note this is now in red because you're going to need it. This is very important. Yeah, put it in red. Okay, that's too thick. So each carbon atom in graphite forms 3 covalent bonds. 3 super strong covalent bonds. These are the same bonds that are in diamond. It's just not making 4 of them. 3 super strong covalent bonds. The fourth, now notice my change in color and capitalization. Please do the same. The 4th unpaired. The 4th unpaired electron. You're not allowed to do that in your exam, by the way. You're not allowed to do this in your exam. You have to write down the word electron. Oh, by the way, Mita and Feffy, have you watched my recent YouTube videos, my sparkle video and my floor is lava? If you haven't, you should definitely watch them. The 4th unpaired electron, change back to red. The 4th unpaired electron becomes, change my color, delocalized. Becomes delocalized, which means disconnected. Yeah, becomes, I missed the S out. 4th unpaired electron becomes delocalized and can flow between, change back to red, and can flow. It's really nice. And can flow between the layers. It's really amazing. Graphite is an amazing stuff. So you pick up this extra diagram. So here are our layers, and the electrons that have hopped off the carbon atoms can now flow between the layers. There's a carbon there, and a carbon there, and a carbon there. They each throw an electron into the sea, and it can flow between the layers, so they can conduct electricity. It's an amazing feat. Graphite is an amazing substance. Very, very cool. Ooh. Ooh. There you go. Isn't that amazing? It's quite a nice picture, that. Quite like that. Quite like that. No. So this now is actually the explanation. Isn't that amazing that we can actually have? So by the way, once that electron hops off, so this is just really for those people who are interested. Once that electron hops off, the shape changes and it becomes trigonal planar. Yeah, this is the shape of this is called trigonal planar. Planar means flat, by the way. So at this point, it changes shape to be a triangle. Yeah. And so the stick diagram over the top. The stick diagram over the top. It's in this triangle shape. Kind of cool, that. But that's actually the most important diagram right there. Learn that one. Let's put it in a bubble. Ooh, like this picture. Love it. So 3 beautiful diagrams of graphite. And this now actually explains the property of conducting electricity. So we've picked up soft, which is the layers. And now this explains, so question, explain why graphite conducts electricity. Conducts electricity. Later on the show. Conducts electricity, and the answer is each carbon atom forms 3 covalent bonds. The 4th unpaired electron becomes delocalized and can flow between the layers. It's really cool. Graphite's amazing. So we have covered it's soft. I'm going to tick these properties off. We've done conducting electricity. We now need to explain, now this one's really, really horrible. And actually, it's going to be difficult to explain this one without having done simple covalent first. But this is a giant, and I am very aware of that. So if we were to explain the high melting point, now guys, you're going to have a leap of faith for me here. So question number 3, explain 4,000 degree melting point MPT of graphite. And we're running Susan Boyle again. Last lesson we got to see Susan Boyle in all its glory because of Lauren. Lauren said to me, "Oh, I'm getting confused." No, she didn't say that. But she was like, "What can you like?" Lauren asked a question, and I then ran Susan Boyle for all of the metals, ionic, and the giants. And this one is exactly the same process: structure, bonds, strength, number, and energy. And this is where you're going to need a leap of faith, I'm afraid, guys. And I'm very sorry for this. So next lesson, this will become much, much clearer. So just to tell you that within the layers, it's nice to mention this. So within graphite's layers, we've got strong covalent bonds in these hexagon structures. Yeah, these here are super strong covalent bonds. Yeah, this is within the layers. Yeah, within the layers are strong covalent bonds. Strong covalent bonds. These are the strongest bonds I have. Thousands of melting points to break. Thousands of melting points, thousands of degrees. Yeah, and then what is between the layers? So between the layers, and this will make more sense next lesson. Between the layers is something I've never mentioned to you yet, but they're coming. Between the layers are weak the word inter literally means between. Intermolecular forces. There we go. Now, when I first started teaching chemistry, I didn't do this little acronym, but I love this acronym now. It's one of my favorites. These I like to call WIMPs. Now, you can't use this in your exams, but you can use it to help you remember weak intermolecular forces. The word internet is between networks connections. Yeah, and this, so the word inter means between. So weak between molecules forces. So between them, so for example, in water, we're going to look at these next lesson. So in water, you have got strong covalent bonds between the oxygens and hydrogens. These are very strong, but between the water molecules, I should do the same color since, you know, continuity. Between the water molecules, we have WIMPs, weak intermolecular forces. So when you turn liquid water into steam, when you boil water, you're not breaking the covalent bonds. They're way too strong. What you're breaking are the weak intermolecular forces, which is why it then becomes a gas, and why the boiling point is so low. We'll be talking about those next lesson. And graphite has them between the layers, which is why they can also slide. The weak intermolecular forces allow them to slide. So to run this question for graphite, run Susan Boyle. So first thing is structure. Graphite, we've got to say that graphite is a giant covalent structure. Giant covalent structure. Now, at this point, I am just going to mention something, which is brackets macromolecular. Molecular. The word macro means big. Yeah, it's the opposite of micro. This is a big molecule. Yeah, but we just call them giant covalent structures. But it's just nice that there's another name for this. It's called macromolecular. We say giant covalent at GCSE, but that appeared on a GCSE paper, which I spotted recently, so I thought I'd add it into my lesson. Graphite is a giant covalent structure. Right. Now, this is where graphite gets tricky, because graphite has two types of bonds. We have to say graphite is a giant covalent structure with covalent bonds, the electrostatic attraction between the shared pair of electrons and the two nuclei, with covalent bonds within the layers, and weak intermolecular forces between the layers. I know, guys, I know it's tricky. I know it's hard. Everyone hates it. I get it. It's mean. I really, really do understand that people don't like this story because that is so complicated. It's not complicated, guys. You've just got to learn it. Right. Strength. The covalent bonds, you ignore the WIMPs now. The covalent bonds, the covalent bonds are very strong. You ignore the WIMPs now. Now here's the clever bit. Number. So we've usually been saying there are millions of bonds to break. There are. We've still got to say that. But the key thing is there are millions of bonds, and all bonds must be broken. You can't just break the WIMPs. Yeah, you can't. You've got to smash everyone. So all the bonds must be broken, including the strong covalents. So the energy. So energy is very high. We're done. Oh, graphite. I know it's mean. 3 questions. 3 questions for graphite, and all of them are just tricky. And guys, I'm very sorry. You just have to learn them. So it forms in layers, and the layers can slide. Each carbon atom makes 3 covalent bonds. The 4th unpaired electron becomes delocalized, like in metals, and can flow between the layers. In metals, we say flow through the structure, but in this, it's flow between the layers. Melting point. Graphite is a giant covalent structure with covalent bonds within the layers and weak intermolecular forces between the layers. The covalent bonds are very strong. Millions of bonds, and all bonds must be broken. So energy is very high to break, to melt. We're done. So I quickly go up to here. So no graphite's properties, no graphite structure, explain the properties. So we understand the solid, it's a high melting point. Oh, color-wise, that's actually a really interesting one. You can also explain that with the bonding. So because graphite has delocalized electrons, those delocalized electrons can absorb visible light, and they absorb all of it. So they absorb all the visible light, and hence why it looks black. When diamond has light shone on it, all the electrons are in bonds, so they can't absorb the visible light, so it's completely see-through. and colorless. Used in pencils because it's soft, and the electrodes because it conducts electricity. It's cool that. If you're wondering about it being brittle, the reason being is if you imagine you taking your, this is just purely for fun now, guys, brittle. I've never seen this in an exam. If you were to have a look at a pencil, this is pencil lead. I've actually, by the way, taken that, like the pencil usually has wood running around this, and I've just taken that away. And if you were to look at the structure, what you realize is it's just layers. Millions and millions and millions and millions and millions and millions and millions of layers. This is why when you then run your pencil, over it, what you're actually leaving behind, just for fun, what you're leaving behind are layer after layer after layer after layer. The layers are sliding off. Isn't that wicked? Yeah, you're leaving behind boatloads of layers. And those layers, of course, it's like a pack of cards. Yeah, you take a pack of cards. Yeah, you got your pack of cards. And your pack of cards is, loads and loads and loads of layers. And if you then take your hand and you push that, what will happen is the layers then, the cards then spread out, but they kind of overlap with each other. Yeah, and so you form this long line of cards. You're doing the same thing with graphite on your, isn't that cool? You're doing that on the paper. You're drawing a line with pencil and you're leaving behind tiny millions and millions and millions of super thin layers. Really cool. You can even prove this. So one of the things that you can do on YouTube, shouldn't really YouTube while it's on YouTube, shouldn't you do that? Graphite paper conduct. So, oh, that sucks. Conduct. Hey, the guy
designing and then constructing a circuit is one of the most tedious yet rewarding things you can do in the field of electronics. However, what if you could just break out a pencil, draw a circuit on a piece of paper, and have it work? Load the lights, and as you can see, it powered right up.
Not wicked.
Obviously, some minor adjustments were needed to get everything to sit right, but the result was a paper circuit.
They're not particularly good conductors because the layers are all kind of smudged over each other.
Not being satisfied with just that, I wanted to up the ante just a little bit more and see if I could MacGyver myself a flashlight using just these materials. After scribbling 2 lines across the paper, I decided I would roll it up into a cone. After that was done, I made some minor adjustments and clipped it out so that the graphite would be visible at both ends. Then, adding a little bit of tape, we were able to seal it up. Now I just took a little bit more tape and added the LED to one end, and then clipped the batteries to the other end. Lumos, it worked pretty well considering what it was made of. I even discovered a monster lurking in the dark.
It's his dog.
So I thought that was pretty cool. MacGyvering.
So now, can I just point out, when he's doing his circuits, when graphite's put onto paper, it's not a particularly, the layers are broken up. They're all kind of slid the way that the cards are. So what he does is, you can see him in the video doing this. Yeah, he's doing this. He's layering on loads and loads and loads of layers of graphite, making it really thick on the page so that he has lots and lots of layers stacked on top of themselves. Yeah, so then he can clip on his LED, and the electrons, of course, can then flow across the page. Yeah, they're skipping over layers because he's drawn on, as I said, he's gone over it and over it and over it. But it is a cool little game, and it can be done. It's one of those things that we try to do in school, but it doesn't always work particularly well. But having better quality graphite also makes everything a lot better. Just to also let you know, pencils are an interesting one, because students often say, hang on a sec, Mr. Duncan, so pencils. Like, oh, Mr. Duncan, I like to draw stuff for me. By the way, I like to draw things too. Oh, I don't know where it's going to be. Did you guys saw my drawings when I was bored one day and was doing some drawings. I think I did them in QuickNote. And I did loads and loads. I just did a couple of I can't remember where they're going to be. It's going to be lost in the depths. Oh, there's one of them. I've actually found him. There we go. Yeah, I was just drawing that on my tablet. So, students sometimes ask me, you know, I like to draw things, and that there's different grades of pencil. Yeah, I know that there's different grades of pencil out there. Yeah, and I was wondering how they do the different grades, considering, you know, graphite is graphite. So how do they do the different grades of pencil? There you go. Different grades of pencil, like HB, and then one B, and then 2B, and then you can also get H2. You can get all these different grades. So what they're actually doing is a rather clever trick. They're taking the graphite, they're taking the graphite and they're mixing it with clay. So the clay makes it harder. It takes away the softness. Yeah, 1 mole in solution. Calculations, you do that after bonding, guys. But anyway, so they add clay to it. So if you want to do the trick you saw on YouTube, you need to have pure graphite. So pure graphite pencil. So you need to make sure that you pick the right type of pencil. Yeah. So I wonder if graphite pure pencil, graphite. Let's see. That's not going to help me very much, is it? So which one's pure? Solid graphite pencil. Pencil grade? Don't know. Pencil grades. Degrees of hardness. You want to go for the softest. So if 9B is the softest, I'm assuming 9B is going to then be pure graphite. 16 different grades of hardness. And I'm assuming if that's the lowest it goes, there you go. I'm assuming that means that 9B is pure graphite. So you'd want to do it with that, because otherwise you're adding clay to your page and it won't conduct electricity because the layers are going to be separated by the clay particles. So you have to be, like, as I said, I've played around with doing that demonstration and that practical with the kids in class, but I have to have certain grades of pencils. Anyway, so bringing us back to today's lesson. So the next thing is, we've got 10 minutes left, and that is graphite derivatives. So graphite is an amazing material, and we've used it for decades because of these crazy properties. But then we started to be able to do some really cool stuff. So subtitle is graphite. Oh, year 10s. Can I ask you, please, anyone who hasn't submitted the homework on the research of alloys, please do. Otherwise, I will mark it as a missing homework, and I will email home. Please do. Score sheet. I can tell you who's missing. Score sheet. So for you guys in year 10. Oh. That's weird. Got something that's unlabeled there. I can tell you who's missing. Mark book. I have graded the others, by the way, and done some feedback, which I will email back to you guys. So I am missing Navina, I am missing yours. Jade, I'm missing yours. Henry, I am missing yours. Gayatri, am I missing yours, Gayatri? Gayatri, I'm missing yours. Vincent, I'm missing yours, and Ian, I'm missing yours. Please get that into me on the classroom, please. Yeah, please, please, please. So, graphite derivatives. So the first thing is derivatives. What does the word derivatives mean? Derivatives. This is new things, new new graphite products. So the first thing I get to talk about now, and I get you to do some research on this as well. This is why I don't want to ask you to do the next research project without this. So the first one is graphene. Number one, I'm going to write it underneath it since, you know, graphite derivatives. There we go. So number one is graphene. Now, graphene is a single layer of graphite, just one layer. Yeah, I'm not going to bother trying to draw that. I'm running out of time anyway. Graphene. So, graphene, nice one. So, graphene is a single layer, just one single layer of graphite. Now, the reason why this is special is because this single layer of graphite picks up a whole new set of properties. So, there's graphene at the 2D. I did the alloys homework and sent the answers over by email. Okay, Gayatri, I just haven't added your scores to it then. I'll do that, don't worry. Thank you for letting me know. So a single layer of graphene. What I kind of want to do is steal that picture. Snip. There we go. Edit, copy. A single layer of graphite. So graphene is very special because it can still conduct electricity, but now it is no longer brittle, and it is now so thin that it becomes actually invisible to the naked eye. This is the future of touchscreens, phones. Yeah. So graphene, super cool. A single layer of graphite. It has still got an incredibly high melting point. I've submitted mine and written it onto the score sheet. Thank you very much, Navina. Thank you very much. So graphene, cool structures. One layer of graphite. One layer of graphite. One layer of graphite. Future uses include touchscreens because it still conducts electricity. Touchscreen phones. 4 phones. Yeah. It's completely transparent. So thin you can't see it. Yeah, it's also as strong as diamond, amazingly. This would be like bulletproof cling film. Yeah, they're going to be incorporating it into bulletproof vests soon as well. It's incredibly tough. It's amazing stuff. Haven't quite figured out how to use it properly, how to create it properly yet, but we're working on it. It's going to be in everything soon. Incredibly high melting point, all that jazz. So there's graphene. Now the next one is even cooler. The next one are called carbon nanotubes. So that's graphene, single layer. Number 2 is carbon nanotubes. Carbon nanotubes. And if you notice, it's really cool. They basically take a graphene sheet and they roll it. Carbon nanotubes. They roll them into a tube. It's really cool. There you go. Look at that. Graphene to carbon nanotubes. Copy image. So these things are going to be amazing. These are electrical cables. These tubes become electrical cables. There we go. That can conduct electricity better than wires, but as strong as diamond, which is amazing, and are super small. So these are going to be used in the future for making electrical motors. It makes them more efficient. It makes them smaller. It makes them lighter. It makes them cheaper. They're amazing things. And the explanation for the conductivity is exactly the same as graphite. Each carbon atom is still only making 3 covalent bonds, and the electron can flow through the tube. Really amazing stuff. Nanotubes. The last one, by the way, still have a melting point as well, which is crazy high. Yeah. Basically like indestructible wires. Amazing. And the last one are called Buckyballs. I know it sounds weird. Buckyballs or Buckminster. It's the guy who invented them. Buckminster fullerenes. Now these are footballs made of carbon. Now these have a low melting point. Something drops now. Buckyballs. So these cool things are these football-like structures that are made from pure carbon atoms. They form footballs. Take a picture there. There we go. And they've still got the carbons making 3 covalent bonds. So the balls are actually full of electrons, which is really cool. Now these are being used as they're being added to car oil to be acting as bulletproof ball bearings. They're very cool things, these. They're also using it for drug delivery. They're putting drugs inside the buckyball. They can then move it around using magnetic fields and then deliver the drugs where we like. Super cool. Drug delivery. Used for drug delivery. Really cool stuff. Delivery. So these new materials are the future of are going to be some amazing things in the future. You know, touch screens that now use graphene, electrical motors, and efficiency of the wires goes up. By the way, carbon nanotubes. Another thing is they're taking the nanotubes down because they're as strong as diamond. They're turning them into ropes, so you can actually get carbon nanotube rope, which is super cool. Carbon nanotube ropes. And they're actually now making them, which is amazing. It's not perfect yet. It's still got problems. Just give me one sec, guys. Still got problems. But they're going to be amazing material, basically an indestructible wire. It's going to be very cool. That can also conduct electricity. It's going to be amazing. So these are all being done. These are the future of materials. I will leave you guys be at this point. I will leave you guys be. Bring you back up to my screen. I hope you guys found it useful. Let's get rid of that. There's my StreamYard. Bring you guys back. Right, I will leave you guys there. I hope you guys have a nice rest of your day. Once all of the alloy homework has been submitted and I've finished marking them and sent them back to you, you can do your research on graphene, nanotubes, and buckyballs. I will see you guys soon.